I think we've covered a lot, so I want to do a little miniature review. Basically, all the thermos, just run through the stuff with little stars on them. And then we're going to get into the 48 variables that you actually have to know for the first test and the second test and the final. And anyway, yeah, so I don't want to scare you, but that is true. Okay, review what we've done so far, and I'm not going to talk about gases. The gases are, the gas equations, we're going to use them to do thermo equations. That's why I spent the first week or two doing van der Waals and all that, because it comes up when we do this stuff, which is understand internal energy, which starts out with the equal partition theorem. And remember, I use shorthand, degrees of freedom. And hopefully this homework, hopefully this is cementing your knowledge of degrees of freedom, where you have, what did I use, acetone this year? Every year I pick a different molecule with a high CV and have you think about degrees of freedom. Just remember that, like on an exam, I'm going to stick with helium having 3 degrees of freedom, O2 with 5. That's because it has 2 rotations, and methane with 6 because it can rotate 3 ways as opposed to 2. That's as much as I would have on the test. Now you also definitely need to know this, that the change in internal energy is going to be the heat and work. And there you go. And now again, this is on the cheat sheet, and I will send that to you Wednesday before the exam. I don't send it before because I haven't necessarily, I'm going to write the exam this weekend. I can spend about 3 days on it. So those of you with last semester's exam, I start with that, then I change all the questions, just so you know. And then I double check my other exams to make sure I didn't rewrite one from there. So anyway, what am I want to say about that? I totally forgot what my point was. Anyway, so I'll write it over the weekend and I have my TAs error check it. So I will only send the cheat sheet the Wednesday because I want to make sure that the cheat sheet represents what's on the test, and I just not really finished it until about that Wednesday. So anyway, okay, now these two combine in such a way that at constant, so all the questions are going to read like a gas expands, a gas contracts, and then there's stipulations. One of the first ones that we have at constant temperature. And for a constant temperature, as you were getting pretty well, the change in internal energy, that won't be a change. And that gives you an inroad to calculating the heat from minus the work. And again, we've already gone over how work works. And that is minus the exterior pressure times the change in volume. But work is path dependent. So we talked about 2 possible paths. One was irreversible, where the integrated change in work is minus exterior pressure. And this is, by the way, this is the easiest of all the types of questions I can ask. Irreversible isothermal is the easiest, and that's because of this right here. This is quite trivial. Okay, slightly harder, although I would contend, so sorry, let me write the irreversible. Slightly more difficult is if it's reversible and done minus nRT natural log, and just look at the videos if you don't remember where this comes from, and this is a reversible. Okay, so I've got 1, 2, 3. I could ask change in volume, pressure, temperature, 4, 5, 6. I've got 6 variables and 2 conditions. That's isothermal, reversible, irreversible. Those are the 2 conditions. I've got 6 variables. Right now, I've got a total of 12. Notice I've got 12 variables: pressure, volume, temperature, and work, heat, and internal energy. So there you go. Remember, we're building up to 48. Okay, now, in this case, I've got heat being minus work, but now if temperature does change, which will be the subject of the rest of today's talk, we know how to relate the heat to the heat capacity, but of course that also depends whether you're at constant pressure or volume, and that's the change in temperature. I expressed it slightly different last time. And remember that these need to be integrated. You don't need to write this down. This is just proper mathematical notation. If you integrate them, you get Cp or V. And of course, the question tells you whether you're at constant pressure or volume. It'll directly tell you that. There won't be any ambiguity. All right, the last bits that we covered last time were at constant At constant volume, there's no work, and so therefore the heat capacity, remember which is temperature dependent, but I'm never going to really make that a big deal. Maybe I'll ask one question, but I generally, the class is hard enough without having to worry about the temperature dependence, so I'm usually just going to knock it off. Okay, there's that, but at constant pressure, of course, what I have to do with CP. CP is irrelevant. Still temperature dependent, still don't care really. And we covered enthalpy. There's this relationship again we did this last time, so it looks like I've got 7 things. Work, heat, internal energy, enthalpy, pressure, volume, temperature. 7 times 2, 14. So now I've got actually 14 different things I could ask depending on how the gas expands and gas contracts. And of course, now I also am going to ask you, gas expands, gas contracts. What is the change in H? And of course, that's the change in U plus the change in pressure times volume. And I think that's on your homework. If we're at constant, Now again, there's really no practical way to change volume and not pressure and vice versa. So that's really, what I would normally like to do is do PdV plus VdP product rule. Just forget it. Do it this way. Change in U plus the change in nRT, and of course N and R are constant, so you have that. And that's why at constant temperature, the change in U is 0, therefore the change in enthalpy is also 0. And I should be including units, so I've lost a point, by the way. This is me being OCD. The equal sign was not perfect, or the world will explode. Anyway, so I should be including units. If you are missing units, you're going to be losing a point. There you go. So this is, again, hopefully you're seeing kind of a roadmap where the gas expands, the gas contracts, isothermally, reversibly, irreversibly. You're going to need work, heat, U, H, final temperature, final pressure, final volume, right? There you go. That's exactly how this goes, and these are the formulas. And remember the homework, this next one is going to start to be heavy. Examples, right? 1 liter, 3 moles, 50 degrees, blah, blah, blah. It's going to be very exact, and you're going to, it's fine to see this, but when you start doing this, it's different. And if you're going to get it wrong, that's great, actually, because then you'll get it right, you'll get it right on the test. So, so that's kind of an overview. Let's review last time, which were thermodynamic derivations. And let me start out with the general. Let me just give a really simple example. And this is where, so I'm just saying that the change in U this is the change in work. And so for some reason there's no heat. I just magically shut it off. And let me give you an example of what I could ask. So therefore the change in U, the change in V is minus P. So that's, again, this is a type of thermodynamic derivation. There's something I really should have brought up before now, and I actually feel pretty bad about that. It's not on the homework. I don't think it's on the homework, but even if it is, I'm telling you now. Notice that I said the change in U was the change in work. Is that the right formula for work? No, it's not. What is it? What should it be? External pressure. I said work is always the external minus external pressure times the change in volume. So I wrote internal pressure with just a P. I'm not going to write INT, all right? I already told you that. Okay, what kind of work is this? No, it's still work. It's just it's just a route. It's what? It's a reversible, right? This is a reversible work. Now, I never specified a route, but now here's the trick. Remember, is change in U, is that exact or inexact? Remember? This is exact. And that means this path, what was I don't even know. Path independent. Okay. Now, change in U again is path independent. The paths were reversible, irreversible. I chose to make the change in U reversible. I could have made it irreversible, but I'm going to choose reversible because, for one, it doesn't matter. I will always get the right answer if I analyze work reversibly even if the question specifically states irreversible. If it states irreversible, I better get my equations for work and heat right. Work and heat are going to change if the path is reversible or irreversible. They are inexact. We covered that on like the first day of thermo. Change in U is path independent. It does not matter how I calculate the work. I choose to make it the reversible path. Even again, I must strongly state this, even if the path is irreversible, it does not matter. You will get the right answer. Now, the reason I'm going to do that is, as you're going to see a gazillion times, if I do it this way, it's going to be easier. What is it? Every freaking question I will ever ask you is going to be done a heck of a lot easier if I choose the reversible path every time, even when the magic cylinder doesn't do something reversibly. So yes, my God, please do it this way. So you guys are still kind of new at this. So you didn't notice that last time when I was doing thermal proofs, I was just writing this for work every time, but you're kind of new at that. But this is why I should have mentioned that last time. Okay, anyway. All right, now what? Now what? Remember that this jazz comes from this formula. And again, I'm just covering what I did last time, where F is the change in U, or it could be the change in H. Right now, that's what you've gotten so far. And remember, I've written this out a zillion times now, and you're going to write it down a zillion times more. And it's going to be so stuck in your head, you'll remember it forever. Okay, I'm going to start with this. And I can see that F is the change in U. The F dx is the change in U with respect to V. Here's my change in V. And the U dV at constant something y is minus P. So this comes from here. So I've asked you, what's the change in U with respect to volume? And what you do is you write the change in U out this way. You get to this, and then, sorry, I really didn't do this in the right order, and then you get to here. Now, one thing you're missing that we're not ready yet is that you have to specify that y is constant. In this case, we're not ready, but it's actually entropy. So for the change in U minus PdV plus, there's an entropy term. We're getting there. We're not ready to do that. That'll be in 2 weeks, 1 or 2 weeks. I don't quite remember. Okay, now, again, I've got you on the test, and you have the harder derivation section, and it's a thermodynamic proof. What's the change in H with respect to, what did I do, P at constant T, yada, yada, yada. You're going to write this, then you're going to divide by another partial, you're going to identify the little bits, you're going to notice that things are either 0 or 1, and then you're going to get the answer. The last bit to notice is that the next question, I tend to give the answer. I said, if du dv is minus p, tell me what the actual change in u is, and that means that you bring over your partials and then you integrate them. Right. So yeah, there you go. And that's really all of last lecture. And we are going to do a zillion more examples. I'm just going to do nothing but examples. And remember that on tests, when it comes to what's the change in this with respect to that, a constant that, I mean, I've got so many letters to choose from that I just never run out of examples. And I did show you an example of how you can write circular. I can come up with problems that will just run in a circle. I showed you that in the last hour. But I am careful. Don't worry about that. I know when you might do that, and I will stop it from happening by setting up the question so that that won't happen. If you didn't watch the last hour, again, you really need to watch that last hour. Okay, so that's all I got on review. Are we okay? No questions? Okay, that's awesome. So let's just charge ahead and get into new stuff. Again, this is still just review. And just remember, there really are just a small number of things that you do need to remember. Those things are on the cheat sheet. But if you really don't have them at heart, like change in use, a change in heat, and change in work, if you don't have that by heart, having it on the cheat sheet probably isn't going to do a lot. Having it in your calculator, which I expect because I did it 20 years ago, I invented that, it's just not going to matter. And that was, it's almost cruel. You know, I mean, it's the same when I took it. You know, I thought I was being clever putting things in my calculator, but it never mattered. So, where are we at? Okay, so now we're doing something new. And I alluded to, I never named it, but I mentioned that we're going to do some transitions with the magic cylinder where it's wrapped in glass wool. And By the way, we're still in chapters, this is section 210 in chapter 3 of the book, whatever. So we're going to talk about more with temperature changing, and temperature changing systems are adiabatic. Okay, and you got to make sure I spelled it right. And this means thermally insulated. Okay, now this is opposed to isothermal. We've got isothermal or adiabatic. In fact, let me make sure that this is spectacularly clear by talking about all the paths and conditions. I've talked about paths being irreversible. And I've also, of course, juxtaposed that against reversible. Remember that these are extrema of reality. Reversible engines are perfect engines, irreversible not so much. And of course, reality is somewhere in between. So, two paths, reality is a shade of gray, but let's not worry about that. I don't even know how to deal with that. Now, we've also talked about isothermal. Okay, and you know that when you see isothermal, okay, you're on the test. A gas expands, really. So a gas expands, a gas contracts, and it says isothermal. I'm going to ask you delta T. Delta T is 0. What's delta U? 0. What's delta H? 0. Okay, 3 points. That's a 30th and F. Anyway, but then you just answer the rest. Just answer the rest and you're fine. Okay, isothermal, and now here's our last one, adiabatic. And I will always write 80 for adiabatic. Problem. Oh God, let me keep this straight because I get confused. Isothermal can be reversible or irreversible. Or I can say, the gas expands, the gas contracts. That's adiabatic and irreversible, or adiabatic and reversible. Okay, so there are 4 conditions. Okay, you get it? Isothermal, reversible, irreversible. Adiabatic, reversible, irreversible. That's a total of 4. Now, there happens to be, of the 4 conditions, what can I ask? I can ask U, I can ask I can't write Q, I have to write the change in Q. I can write the change in word. I can ask about H and the change in H. I guess I should write that down. I got P, V, and T. I'm going to keep N constant. R is by definition a constant. I might need to figure out the heat capacity, constant volume, the heat capacity, constant pressure. And as you're going to see later, this is what we've covered so far. I got entropy. I got something called A, and then G you're familiar with. Okay, so that's 12 times 4. That's 49 possible changes, right? 48, that's just trying to see if you're paying attention. Right, 48. Okay, now remember I've been saying a couple times today and previously, there are 48 possible answers to the question depending on how the question is set up. This is the setup, this is what I'm going to ask, but then there's 4 permutations. Yeah, that kind of blows, but remember, I'm going to have a little star, like everything I just covered gets a little star. It's on the cheat sheet, it's not that bad. And plus, remember, there's overlap. Isothermal, the change in U is 0, whether you're reversible or irreversible. The same for H, okay? That's 1, 2, 3, 4, 5, 6, 7, 8 that's 4. Sorry, that's 4 possibilities with 1 answer, right? You see, we can whittle these down. Yeah, anyway. It's not so bad, but as I told you, I want to tell you the truth, but I don't want to freak you out, but not by not telling the truth. I mean, this is the truth. So, anyway, all right, now let's get into what does adiabatic mean. I'll toss this up. And so, basically, for adiabatic, again, all this jazz we've covered, except the magic cylinder is not made of metal. It's made of metal, but it's wrapped in glass wool. And so that, unfortunately, changes everything. In terms of all these, U's and Q's and W's and H's, temperatures and pressures, definitely temperature, right? Because isothermal, again, that one's brainless. And I will actually, when you see that, when I say something expands isothermally and I ask what the change in T is, I'm just giving you a point, right? So don't second guess yourself. I like to give you points. Okay. What do I want to say? Okay. So adiabatic, remember, means that's covered in glass wool. I think I hopefully spelled wool correctly. That's always a weird word to me. And let me give you an idea how this is ultimately going to work. Okay, the magic cylinder, all right, the magic cylinder, let's do the magic cylinder, and I'm going to push, and I'm going to compress the gas. Does the gas get hot? Hot or cold? Hot, right. When you compress a gas in a magic cylinder, it will get hot. But it was made of metal, and heat was released to bring it back to the same temperature, right? Metal things get hot, and they cool back down. Okay, work, positive or negative. Again, compress the gas, storing energy. Positive or negative? What is the energy bank? It's positive to do what? Store energy. When I press on the plunger and pressurize the gas, that's storing energy because it can do more work later. Positive work. Okay, heat. Positive or negative? It's the opposite, so it's negative. Right. I'm touching it. Is it hot or cold? Of course it's hot. The gas got hot, it gets hot, and then of course it dissipates into you. That's why you feel hot. Okay, so you know that. Now here's the trick. Now I'm going to compress the freaking magic cylinder, but it's wrapped in glass wool. Now the gas is going to get hot, but stay hot. And that unfortunately changes all the equations, and just kind of something you need to remember. Okay, in terms of things that get a star, adiabatic means dq is 0. Okay, that's automatic, and I need to write units. I don't know why, I'm really forgetting to do this today. So if it's wrapped in glass wool, there will be no heat transfer. Okay, so that's critical. But now this is where, personally, I have an intellectual conundrum. What you've got to remember is that there's still heat inside of it. This is heat transfer. It doesn't mean that, and literally I've had students say, if I wrap, here's the question, I wrap the magic cylinder in glass wool, what's the temperature in the inside? And they said, well, it's got to be 0, because there's no heat. 0 K? That's crazy, right? You wouldn't never forget that. You just, let's wrap up your little brother. Now he's frozen and you're a murderer. But so that does not work, right? So things still have heat and they will do transitions with that heat. So what happens is the magic cylinder, here's a question I'm going to ask. The magic cylinder is at equilibrium. I wrap it in glass wool and then I add a lot of heat. And the heat doesn't dissipate because it's wrapped in glass wool, and of course the magic cylinder expands, and you give me all that jazz up there, right? That's the kind of question I'm going to ask. Now note that there was no heat transfer. I had to use the force to add heat, or maybe wires or something, but anyway, you get the point. There was still heat inside of it, and that heat did something. It caused the magic cylinder to expand. So while there's no heat transaction, there is still heat inside of it. And that also means that the thing that you have to get, and this gets a big star. And again, the whole point of all this is calculate all this jazz. You're going to do it almost entirely one way. Calculate the change in temperature. Do this first, because that's a free point, and that's just me giving you something. The next thing is do that, because once you do this, you get the rest. But you must do this first. Everything depends on calculating the change in temperature when we have an adiabatic magic cylinder. Okay, so, and notice that, again, the temperature changes because while there's no heat transaction, there's still heat inside of it. So it's going to use its internal heat to do stuff, and that's the standpoint by which you have to figure things out. So again, now, just to be practical nuts and bolts, let's start whittling our way through that giant list bit by bit. So the adiabatic cylinder has done something. Now give me all the stuff I could possibly ask. Again, it'll be listed out. Now normally I would say this is what? It used to be 0, now it's not. Okay, I start here. Can I simplify this? All right, do this, get rid of that. There you go. It actually doesn't look so bad. That's not correct. It is bad. There's a reason I do this one last. Okay, this will be minus for irreversible, and it will be equal to minus PdV reversible. Okay, so I've told you about the magic adiabatic cylinder. If you can just calculate this sucker, you get that, and you get that. You're almost there. Question?
Does it change if you go to 0 or 1?
0 or 1? What?
The change in Q, you crossed it out.
Oh, 0, 0, yeah, sorry, right, yes, 0. Right, 0.
Oh, it's 0.
Yeah, 0. And that's by definition. Okay, now, again, the point is, I've told you a lot about the magic cylinder. Obviously, I have to use something to answer the question, and I'm pretty careful about that. And it seems like, well, okay, well, you know, whatever the pressures and the temperatures are, and yada, 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 I should be able to do this, and I get that and that. And then, of course, there's probably some trick for delta H as well. It looks like we're on our way. That's wrong. And that's wrong because of this course show. Now, we're going to use P equals nRT for adiabatic transitions. And if I'm feeling very difficult, maybe we'll incorporate van der Waals. I've never actually done that, but anyway. Okay, now remember, again, I can't emphasize enough. We're trying to get to this, and I have this, and again, I will make the gases perfect. And previously, see, this just wasn't so hard because remember that the magic cylinder changes because I'm pushing on it, or I pushed on it and then I let go, and things move, and move means changing volume because I've changed, I've pressurized it or depressurized it. So this isn't hard. Whatever I've done here, and I had to tell you what I did. Remember, things move because you're pushing or pulling, and I have to tell you that. Then you just get to that, and then you have that, and then you have that, and that. Problem. One equation. This is changing. This is changing, and yes. Uh-oh. So if I double this, you can't just have that because this could absorb some of that. How much? You don't know. Seriously, you really don't know. Just not this way. So all those tricks I had at constant temperature to figure out P's and B's, which then give me everything else, they don't apply anymore. You can't do them. Here's the crazy thing. This equation still works. It's just that I can't use it practically. I can't use one equation, here's something changing and here's something changing, right? That's a 1-to-1 ratio. I have one equation. That's fine. But when here's something changing equals to two things changing, no, that does not work. You've got one equation and two unknowns. You cannot solve it. So that's ultimately the problem here. Okay, so let's forget this. Do recall, though, that PV equals nRT still works. I just can't use it for anything. At least not now. Okay, all right, hold on. Let's back up. All right, we're still trying to get to this. All right, the first thing that we have that we can possibly answer, and I can't do it because temperature is changing and this doesn't apply. Okay, so here's a little graphical way for you graphical people to think about this problem, is that I'm going to give conditions, I'm going to tell you in some snarky way how the volume is changing, and of course the temperature is changing, so let's do an expansion, which gas is cool. And we're going to calculate the change in U for that process. And I'm stuck, right? That's what my issue is. I'm stuck with all the stuff that I know. Now, change in U, I always thought this was really clever. Right? Change in U is path independent, and I can follow any path, right? You remember when we did inexact partials, and I kind of drew something just like this? If I do that, then I can separate the change in U into two components. Let's do this first one, which is an expansion. So there's a lot of Yoda using force here. And what's happening is the magic cylinder is wrapped in glass wool. It's under pressure, however that happened. And now the plunger's let go and it expands. Yoda, who is path independent, allows it to expand, but the temperature to not change. Now that has to be compensated in the second step, but we're not there yet. What's the change in U? It's what? Why? It's what? The volume is changing, but what's not? Temperature. Now, of course, we have to use the force to do it, but whatever. It's path independent. Here's the crazy thing about these path independent exact things, is that you can even make up things to answer the question. Again, a cylinder expanding, the gas will cool. But I can use Yoda to make it not cool, as long as I end up at the right endpoint, that's okay. In other words, I can make stuff up and still get the right answer, and that's very useful. Okay, notice now that the change in U is just this part, which is a cooling at constant volume. Oh my God, how do I do that? What? Someone tell me how to turn a change in temperature into a change in energy. Someone recall the thing we talked about last time.
Work is zero.
No volume. Okay, work is zero, right? Okay, work is zero.
So it's delta Q.
Delta Q. Now give me a formula for Q. Okay, recall the last lecture.
You allow work to happen, you allow it to extend.
No, this already happened here, and there's no change in U because it's isothermal. This is a heat transaction at constant volume. Now, there is no formal change in heat, but regardless, when we covered heat transactions, we came up with a formula to relate changes of temperature at constant volume to the energy. What did you multiply it by? Heat capacity. CdDT. Right. There you go. Now, here's the funky thing. Remember that this is the formula for heat at constant volume. Heat is formally zero. Heat transaction is formally zero. This is a thing that personally sticks me every time, but in all honesty, maybe because I'm covering it right now, the class has never had an issue. Despite the fact this is zero, you still use the formula to get the answers. And that kind of bothers me, but I know it works. And again, because of Yoda's force using path independence, there you go. So, and that's why I'm saying you want to remember that just because the heat transaction is zero doesn't mean that the thing still doesn't have heat and the heat doesn't do things. And this is it right there. That's all there really is to it. So, yeah, there you go. Okay, so last bit. Now remember I said you have to get the change in temperature. Okay, now I've got a formula for the change in U. Okay, let me just write that here. I've already written it down. Okay, so now I've got a formula for the change in U, but I see that I've got to get the change in temperature. And you see this is going to work a little bit opposite. Instead of getting work to U, I'm going to get U, then I'm going to get work. Whatever, okay. Regardless, I've got to get the change in temperature. So again, you're on the test. A question says the magic cylinder is adiabatic and something happens. You write this down. The next thing you do is you do that. So you get U and then you get work, and then of course we're going to do heat and all that jazz. But you can see my original point. Nothing happens until you get this. Without this, you're stuck. And which means you answer a different question because you have a choice, right? Okay, change it. Now I got to get the change in temperature, so let's do that. By the way, I do have three of you did not pick up your homework, so I have that up here. Now also, when it comes to changing temperature, unfortunately, this is where reversible and irreversible rear their ugly head again. So I'm going to have to do two formulas for the change in temperature, depending on whether you're reversible or irreversible. And I'm going to do irreversible first, so adiabatic, irreversible. Adiabatic, irreversible, then I'm going to do adiabatic, reversible. And by the way, before the first test, or second test, whichever one, what I do is I'll do the board 4 times, each board, where I'm going to do isothermal, reversible, isothermal, irreversible, adiabatic, irreversible, adiabatic, irreversible. And I'll write down all the equations for that. So anyway, it's coming up. Don't worry about that now. Okay, now to get to the change in temperature, what I'm going to do is forget this right now, just changing U. Okay, this is important because there's my change in temperature, the thing I'm telling you you have to get to. And let's relate this to the change in work. And again, I'm using the irreversible formula. Now, again, don't worry about U. Let's do this. Integrate it. Remember, partials are meaningless unless integrated. And I get this wonderful formula. Now remember, never forget, folks, I always give you heat capacity per mole. And so you got to remember to get the heat capacity per mole and multiply by number of moles, which I will also give you. And fortunately, these integrals are relatively easy, so there you go. All right, so all you have to do is figure this out, and now you got delta T. And then again, I'm going to go over it, but then with delta T, you get everything else that we covered. And I'm about to go there. We just need to think about this. See, let's see, what do I want to say here? Here, let me write this out a little bit more to make this a little bit clear, because see, folks, there's actually a slight problem that's probably not clear right now, but there is a slight problem. And let me also tell you that I will have given you these, so I always have to give you enough to answer the question. I'm not going to give you an inch more, because that's what you get on your standard test. I'm going to give you exterior pressure, the initial, let's call that P1. Now that's initial pressure. Of course, I have to give you the number of moles. I have to give you the initial temperature. I give you R, the gas constant. I think that's a given. And that's it. Okay. Okay, so, sorry. And I have to give you CV. Sorry, my bad. If I just tell you the gas, you look it up. No, I'm not that cool. I'll prove the information. So anyway, okay, given you're looking for, right, delta T, that's what you're looking for. Given, not given, but that's the target to begin with. Given, they're not there. They're not there. Now remember, the whole problem with PD equals nRT was one equation and two unknowns. Looks like I just screwed you. One equation and two unknowns. How do I solve that? What's that?
Change it to one.
Change what?
You have two unknowns, so.
Well, or do I? Or have I been snarky up there?
For V1, couldn't you just use P1 and T1 and then just...
Yes, exactly. I have given you the information. I've given you the information. Of course, it's nRT1 over P1. Of course it is. Right? I did give it to you. Now, same problem. An unknown and an unknown. That still doesn't work. Right? If you're going to calculate that something over here, you have to have everything over there. You really got to have actually just one unknown to solve the freaking equation. Or have I given this to you? Okay, using this logic, what do you think goes here? Sorry, here. It looks like this. It begins with an...
Instead of P1, use P external.
Yes, right. So what I was hoping you'd start to blurt out is nRT2, and instead of P2, right, use external pressure. Because why does the cylinder stop expanding? Because the external pressure and the internal pressure are equal, or vice versa, right? Okay, so now notice what I've done. Let me make this a little bit neater. See, I always I actually don't ask too many of these questions, because what started out actually looking relatively easy, remember, delta T, get to first. And here's the simple equation. Well, it ain't so simple, is it? So, notice that I said you have to get to T2 and everything else is given. Notice the calculator nightmare, wrist-hurting mess that this actually is. Now, again, I don't ask this question too often because it is relatively straightforward. I am going to ask it on a test, on a homework. I'm definitely going to have it on homework. I may have it on a test. But notice that the challenge here isn't so much figuring it out as much as keeping all these numbers straight. Because look, see, you got T2 here, you got T2 here, and you got to get T2 equals. It's an algebraic mess. I do need to know that you can do it, because if you can't use a calculator, really? So anyway, okay, last bit. And so once you get to T2, you got the change in U and you got the change in work. So there you go. Last bit, because we're running out of time, I do need to do reversible. And actually, let me use a new board. And as you hopefully figured out, we got the same problem. It's just calculating the change in T. And what we're going to end up with is a different formula for the change in T. So the lesson here is that the adiabatic cylinder temperature change depends on whether it's reversible or irreversible in terms of how I, do I push all at once or do I push slowly? Whatever. Okay, so the ending temperature is different. And that's because I have a different formula for this. In which case, CV dt is minus PdT. Okay, and I have to integrate this, but since the external pressure is not constant, and it's in fact equal to the internal pressure, what I have to do is this. Just like before, just like in the other reversible case, nRT over V. Okay, and as you did on the homework, you need, if you're going to integrate T's and V's, the T's and V's need to be on the same side, otherwise it doesn't make sense. So I've got CV, and I'm going to go ahead and divide by NR. Sorry, what am I doing? nRT dt. So what I did is I just took this over here, minus dV over V. Again, just the rules of algebra. I have not done any trickery other than middle school algebra. Now the trick is integrate both sides. And of course it'll be T1, T2, Ti, Tf. I told you I tend to screw those up. And there's not much to it, so I get CV over NR can come outside because we're not going to consider the temperature dependence of CV, not really ever. Okay, now again, first Friday, if you've forgotten, I told you all the calculus you will ever need. Integral of 1 over x is ln x. If it's a definite integral, then it's ln t2 over t1. Don't forget the minus sign. Okay. And actually, I'm done here. This is actually enough for you to calculate T2 because, again, I've given you, I would have given you everything you need here. Although I made a big hullabaloo about V1 and V2, they can be figured out as before. But tell you what, there's actually a lot of simplification. This is kind of awful. It actually looks worse than that up there. So we can actually simplify it. And one way to remember this is, if you don't remember these little identities of natural logs, you should have seen this before. But I'm going to use this identity to simplify things. And if you don't quite remember this, you should have seen this before. If you don't remember it, you plug in numbers in your calculator. Okay, so this is just a bit of an aside. So what I'm going to do is I'm going to eat that minus sign here and flip the V1 and V2. It just got rid of a minus sign. Just look, any bit helps. Minus signs are extra bits, so let's not do them. And I also know that there's another identity, which is A ln B is equal to ln B to the A. Again, if you're not sure and you think you need it on a test or homework, plug the numbers in your calculator. And now I've got is ln T2 over T1 and the CV over NR. Almost done here. Question?
So what's given this question? How will they give it? Say?
Well, yeah. Now, in terms of what's given, I know I kind of made a big deal about giving you these things. Just trust me that depending on the question, I give you everything you need. So in adiabatic reversible, I'm probably going to give you V1 and V2 maybe directly. If I'm doing adiabatic irreversible, probably not. I tailor everything, right? And I often do things like, here's another hint. I'm not saying I did it on the last homework because I don't remember, but I often like to make final temperatures 298.15, 273.15. Sound familiar? right? Not 4 billion degrees or minus 4 billion degrees, right? If you see something like that, you probably did something wrong, because I don't like giving hyper-realistic answers. But anyway, okay. Last bit, here's another identity. ln(a) is equal to ln. If the natural log of something is equal to the natural log of something, what do those somethings have in common? They're equal. Okay, therefore, T2 over T1, CV over NR is V1 over T2. V1 over V2. There you go. Okay, so and again, I have made certain that I have given you everything you need. Now, in terms of, if the question was just asked, what kind of snarky starting conditions could I give? Real quick, I just want to point out that I can do stuff like this. I can give you this information. But let's say I gave you pressures. I can do this, NR T1 over P1 over NR T2 over P2. I can give you this, in which case, let me go ahead and continue this derivation. Sorry, I'm doing this too quickly. What I have then is T2 over T1 CV over NR. You can actually prove a lot of these. What would I have? I have P2 over P1, T1 over T2, and therefore T2 over T1. I'm just doing this off the top of my head. Okay, I'm just doing some algebra in my head. Anyway, I actually have a handout of everything I just did prepared. Notice that you didn't have to write all this down. I'm going to post that right after class. Let me give you one last bit right here. You can actually simplify this a little bit. And hopefully you know enough algebra to do this. But there's all kinds of ways to write these. This is essentially an adiabatic equation of state as opposed to PV plus nRT. What's CV plus NR? Is heat CP, right? So T2 over T1 to the CP over NR is P2 over P1. And look, you can change these temperatures to volume to do volume and pressure. There's all kinds of permutations. I'm going to show you an example, and maybe on the final exam I'll have you do something like this yourself. But anyway, remember that top guy up there? That one's important, but just note that you can make all kinds of other derivations of the same. That's how you get P2, and then you got U, and then you got work, and there you go. So next time we'll cover these in more detail.